Hello everyone, I'm Jiayu. I'm going to introduce our work, Self-supervised learning of depth inference for multi-view stereo. This is a joint work with Jose and Miaomiao. Multi-view stereo aims to reconstruct the 3D model of a scene from multi-view images. It is a fundamental problem for computer vision and has many applications such as 3D reconstruction and virtual reality. Recent supervised multi-view depth estimation networks have achieved promising results. Many of the current best-performing methods are cost-volume-based supervised deep neural networks. Similar to all supervised methods, these networks require a large amount of ground truth steps as training data. However, collecting a large amount of multi-view depth data is labor-intensive and time-consuming. The use of synthetic data is considered a good alternative to handle the main challenges in collecting training data for MVS. However, synthetic data inherently have domain problem. Another alternative is unsupervised learning, which use image reconstruction loss to supervise the training process. However, this training strategy heavily relies on image color's photometric consistency across views, which is sensitive to illumination changes and occlusion. Here, we propose a self-supervised learning framework for depth inference from multi-view images. Our method can achieve performance similar to its supervised counterpart without requiring ground truth depth training data. Our goal is to generate high-quality depth maps as pseudo-depth labels for training the network itself iteratively. We generate an initial set of pseudo-depth labels from an unsupervised network and then improve their quality with a carefully designed pipeline to use them to supervise the network itself to improve performance. Our self-supervised learning framework consists of 3 parts: the unsupervised initialization, the iterative self-training, and finally the inference. In the first step, we learn to estimate depth maps as initial pseudo-labels under an unsupervised learning framework. Inspired by networks designed for view synthesis, we directly synthesize image from the probability distribution of depth hypothesis. We generate an image intensity volume for each of the source images and then obtain the synthesized image as the expectation of warped image intensity. For the unsupervised loss function, we use a weighted combination of 4 loss functions. Unsupervised learning relies on the image reconstruction loss, which is sensitive to illumination changes. The initial pseudo-depth label estimated by the unsupervised network is subject to a certain noise level. We propose to improve their quality with a carefully designed pipeline to obtain high-quality pseudo-depth labels for self-training. Specifically, we refine the initial pseudo-labels leveraging depth information inferred from higher resolution images and neighboring views. Firstly, to select the reliable depth labels for self-training, we apply a cross-view depth consistency check utilizing depth reprojection error to measure the pseudo-depth label's consistency. We only use pseudo-depth labels that hold the depth consistency on multiple views. To improve the accuracy of pseudo-labels, we propose to refine the initial pseudo-depth label by using information from a higher resolution training image. As evidenced in our backbone network CVPR, a higher resolution image carries more discriminative features. We extended the coarse network to a fine network to further refine the pseudo-depth label's accuracy. To improve the completeness of pseudo-labels, we utilize depth labels estimated by neighboring views to produce a more complete pseudo-depth map. We first project points from multiple views into the world coordinate system to form a pseudo-point cloud. We then further complete the pseudo-point cloud with screened Poisson surface reconstruction to obtain a pseudo-mesh. And finally, we render the pseudo-mesh back into each view to obtain a complete pseudo-depth map for self-training. The self-training loss is defined as the L1 distance between estimated depth map and the pseudo-depth label. We apply this self-training pipeline for a few iterations to gradually improve the network performance. The network trained by our proposed framework can be directly used to inference on new data. We use the proposed self-supervised learning framework to train a CVP MVS net on the DTU training dataset. We do not use any ground truth depth training data. Our method outperforms existing unsupervised MVS networks by a large margin. Furthermore, our method can achieve similar performance compared to its supervised counterpart. Here are some qualitative comparisons on DTU dataset. Our method can achieve better completeness compared to existing unsupervised networks and can achieve similar reconstruction quality compared with its supervised counterpart. We also directly test the model trained on DTU dataset on tanks and tempos dataset without any fine-tuning. Our result clearly outperforms existing unsupervised MVS networks. Fine-tuning on tanks and tempos training data can further boost the performance. Our code is publicly available on GitHub. Thank you for your listening.